Okay, so we're going to talk about cosets and factor groups. And this quote here at the beginning is supposed to introduce the idea that groups have layers. Or you could think of them as slices or layers, something like that. Now we've seen subgroups inside a group, and what we can do is we can create, in some sense, copies of this subgroup and use those to slice up the group. And these different copies themselves sometimes form a group. And we'll develop these ideas as we go along in this chapter. All right, now, the idea of coset brings together two ideas we've seen before: subgroups and equivalence classes. So we'll use an example that we've used a couple of times. In fact, it was the example we used to introduce equivalence classes. A modular equivalence. So remember that two numbers are modular equivalent, mod m, if their difference is an integer multiple of m. All right, so for instance, 3 and 8 are equivalent mod 5 because 3 minus 8 is negative 5, which is a multiple of 5. All right, so hopefully you're familiar with the idea of modular equivalence. 6 and 13 are equivalent mod 7 because 13 minus 6 is 7, multiple of 7. Right? So we can use this equivalence idea to, basically this is an equivalence relation. We can use this equivalence relation to give rise to equivalence classes. So here's some examples of equivalence classes. The integers equivalent to 0 mod 3 are all multiples of 3. The integers equivalent to 1 mod 3 are all multiples of 3 plus 1. So every element in this set is 1 plus an element in this set. The integers equivalent to 2 mod 3 are this set, which in fact every element in this set is 2 plus an element in this original set, which is the equivalence class of 0. Now notice something. This first set here is in fact a group under addition. It's closed under addition. If I add two multiples of 3, I still get a multiple of 3. But these other two are not groups. For instance, if I take 1 plus 4, that gives me 5, which is in this group here. So those two are not groups. But I do have one group here, which is a subgroup of my group of integers. So I'm going to introduce a way to write these sets. First of all, I notice that the equivalence class of 0 is a subgroup, which I can write as 3z, the multiples of 3. I also notice that every element of this equivalence class is 1 plus an element of 3z. So I simply write this second equivalence class as 1 plus 3z. Right? So just looking back here again, you can see that every element of this second equivalence class is 1 plus an element of the equivalence class of 0. Similarly, for the third equivalence class is 2 plus some element in the equivalence class of 0. So this gives me a notation, 1 plus 3z, 2 plus 3z, for these two different sets, which are going to be what we call cosets. The pattern here is that we take a group element, and then the group operation, and then the subgroup that we're using to define these sets. Now, here I took the group element first and then the group operation, but we know some groups are not abelian. Some groups are not commutative. So I would get a different result in some cases if I took the subgroup first and then the group operation and then the group element. Okay? That would be this notation here. I take the subgroup element and add the subgroup and then add a group element. Now this group element is not necessarily in this subgroup. Right? So here we have two different patterns. This pattern is called the left coset notation, and this other pattern is called the right coset notation because the particular element here is on the right, whereas the particular element here is on the left. All right. Now, up above we were using the operation of plus because we were looking at subgroups of z, and z is an additive group. And we were obtaining cosets by taking a particular element of z plus all the elements of z3, or we could use some other subgroup like z5 to use the equivalence relation mod 5. So as I said, we set up here, we had the group element, group operation, and subgroup. But not all groups are additive. We can also define cosets for groups that are not additive. In that case, we write cosets in this way. So here we go through the definition. Let G be a group and H a subgroup. The left coset of H with representative G, where G is an element of big G, is defined as the following set. It's written as little g big H, and what that means is take all possible products of that element little g with every element in the subgroup big H, little h. Every element in the subgroup little h. So big H is a set, and this notation means take every element of that set, big H, and multiply it on the right with this particular element G from the group big G. Right cosets are defined similarly, where you take every element of the group subgroup little h and multiply on the right by the particular element G. Okay. All right. So here we have, so we talked about left and right cosets. Now let's look at a case where we don't have addition and we also don't have abelian. Here we have H is a subgroup of S3. Remember, S3 is the triangle group. S3 is the same as D3. It's also the group of permutations on 3 elements, and S3 has 6 elements. So here's a subgroup of S3. In fact, if you think of S3 as the triangle group, these are the 3 rotations of the triangle. If you just draw a triangle, well, let's draw the triangle here. If I have a triangle like this, 1, 2, and 3, right? The rotations are going to be, well, 1 goes to 2 goes to 3, or 1 goes to 3 goes to 2. Okay, and those are 2 rotations. This is in cycle notation, and then I also have the identity. So these are all the rotations. Now this is the group of rotations. Okay. All right, so to find the cosets, we should take each element here and multiply it by, we should take each element of S3 and multiply it by these 3 permutations. Okay. All right, now, suppose I do that. Now remember, I have 6 elements in S3. So suppose I take the identity element times this group big H. Big H, again, has these 3 elements. All right. Now if I take the identity element times every element in H, nothing's going to change. I'll just get the same 3 elements back again. But suppose instead I take 1, 2, 3, this rotation 1, 2, 3, times every element in H. Well, you can work out that if you take 1, 2, 3 times each element in turn, well, 1, 2, 3 times 1 is just 1, 2, 3. 1, 2, 3 times 1, 2, 3 turns out to give you 1, 3, 2. Because 1, 2, 3 is a rotation by 120 degrees, and if I rotate again by 120 degrees, I'm going to get the 240-degree rotation. Finally, 1, 2, 3 times 1, 3, 2 gives me the identity. So if I multiply every element of H here by 1, 2, 3 on the left, you can work it out, as I just indicated. You'll get the same 3 elements. Listed in a different order, but it's still the same set. All right, and it turns out, again, you can work it out, that if I take the permutation 1, 3, 2, which is the 240-degree rotation, and multiply by every element of H, I'll get these same 3 permutations in a different order, but it's the same set. All right. Now here I've chosen 1, 2, 3 particular elements of the group S3, but S3 has 6 elements. Let's try some other elements of S3. Well, S3 also has the transposition 1, 2. Now if I take 1, 2 times each element in this subgroup, well, if I take 1, 2 times the identity, I'll get 1, 2. If I take 1, 2 times 1, 2, 3, turns out I'll get, let's see, I think I'll get 2, 3. If I take 1, 2 times 1, 2, 3. And if I take 1, 2 times 1, 3, 2, I should get 1, 3. So in fact, I'll get these 3 elements if I multiply all the elements of H on the left by 1, 2. All right. Now I also need to do that for 1, 3 and for 2, 3 to find all the cosets. And it turns out, amazingly enough, that 1, 2, 1, 3, and 2, 3 all give the same left coset. So in fact, there are only 2 left cosets, and each coset can be expressed in 3 different ways. Okay. These are left cosets. Now I could do right cosets as well. The computation is similar. Take this set H and multiply on the right by 1, and that will give me 1 coset. Of course, if I multiply on the right by 1, I'll get the same 3 elements. I can get another coset by multiplying on the right by 1, 2, 3, and it turns out I'll get the same 3 elements resulting, and H times 1, 3, 2, same difference. And then here also, if I take these right cosets, H with 1, 2, H with 1, 3, H with 2, 3, these are 3 separate computations, but in each case I'll end up with the same set. Okay. So it turns out in this case that the left coset, there are 2 distinct left cosets and 2 distinct right cosets, and they happen to be the same. Now I'll just warn you that this is not always true, but it is true in this case. All right. So here's a case where we do not have the equivalence that we saw before. Here I can take S3, I can take a subgroup that consists simply of 2 permutations, 1 and 1, 2. I could take left cosets. Now you should be able to work this out. If I take, again I have to take all 6 elements of S3 and try them all and see what happens. So if I take 1 times K, I'll get the 2 elements 1 and 1, 2. If I take 1, 2 times K, well 1, 2 times 1 will give me 1, 2. 1, 2 times 1, 2 is going to give me 1. So I get the same 2 elements, as I said, listed in a different order, but the same 2 elements. All right. If I do 1, 3 times K, I'm going to get 1, 3 times 1, which is 1, 3, and 1, 3 times 1, 2, which is 1, 2, 3. And 1, 2, 3 times K will give me the same thing. So I'll work it through, and I get these 3 distinct cosets where each coset is obtained in 2 different ways by multiplying through the group. On the other hand, the right cosets, if you do the right cosets, it turns out that the right cosets aren't all the same. This right coset is not the same as this left coset. All right? So this paragraph underlines the fact that when we compute cosets, it turns out that we obtain the same coset in multiple ways. And this makes the computation somewhat easier. This also shows that the right cosets are not necessarily equal to the left cosets. Okay, so in order to get very familiar with cosets, I'm giving you some chance to practice computing right and left cosets. All right. Now this talks about right and left cosets of abelian groups, and this exercise asks you to show that if you have an abelian group G, that is the commutative group, then any right coset is also a left coset. So you don't get this case up here where the right and left cosets are different, but if you have an abelian group, the right and left cosets will always be the same. All right, so let's stop there.